Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you have a really cool looking analog ammeter that you want to be able to use to measure voltage. Well, this is exactly what I'm going to be talking about today in this video. If you have questions or comments, please feel free to add a comment to this video. I make a decided effort to respond to every comment. If you find this video helpful, please click on the like and subscribe. Don't forget to subscribe. So let's jump right into it. First of all, if you're not familiar with how to read an analog meter accurately, see this other video up here. I've put the link up into this upper corner. The first step in the process of designing your voltmeter is to choose the ammeter that you're going to be using to create the voltmeter. When choosing your ammeter, you need to keep in mind that the voltmeter will be drawing current from anything that you connect it to. This is called circuit loading. The more you load the circuit, the more the meter can affect the operation of the circuit, and the less accurate the measured voltage will be as compared to what it really is when the meter isn't connected. This loading effect is specified in a meter's ohms per volt specification. The higher this is, the less current it will draw and the less loading you get. If your voltmeter is rated, let's say, at 20,000 ohms per volt, and you're reading something on the 5-volt scale, you multiply the ohms per volt times the full scale voltage, so it's 20,000 times 5 volts. The resistance of your meter is 100,000 ohms on the 5-volt scale. So at 5 volts, your meter will draw 5 volts divided by your 100,000 ohms, or 50 microamps. Now, this seems like a very small current, but it might not be, depending upon what you're trying to measure. For the most accurate meter reading, you need to use a very low current meter to create your voltmeter. Now, to calculate your ohms per volt given a particular meter movement, we can use this formula. And so we have ohms per volt is equal to 1 divided by the full scale current of your meter movement itself. So in this particular example, it would be 1 divided by 101.14 microamps, which means that our voltmeter that we're going to be creating here will have a 9.887 k ohm per volt, which is okay. Well, if you haven't done it yet, you'll need to characterize your ammeter before you can continue with this design. You need to know its internal resistance and its full scale current. To do this, see the video. I've put the link up in the corner up here for you. Now, I've already characterized the meter that I'm going to be using for this demonstration. I discovered that its full scale current is 101.14 microamps, and it has an internal resistance of 772 ohms. It's a salvaged meter with 2 scales, 0 to 50% modulation and 0 to 10 microvolts. Now I'm going to use this to create a meter with a 10 volt full scale reading to utilize the second scale of the meter, ignoring the micro prefix. Now I could use this same process to create anything I want. Maybe I want to create a meter that has a 3,000 volt full scale reading. The process is the same. The values we end up with would change. Now, I've known folks that made their own custom scale to go with their meter and replace the one native to the meter. You do not have to use the existing scale. So how do we calculate the values we need? Let's begin this process by calculating the voltage across the meter when we've put enough current through it for a full scale meter reading. The voltage across my previously characterized meter at full scale can be found by the current at full scale times the internal resistance. Now I found my current at full scale was 101.14 microamps, and the internal resistance was 772 ohms, giving me a voltage at full scale of 78.08 millivolts. Now the object of what we're going to be doing is to set things up so that when 10 volts is applied to our voltmeter box, only 78.08 millivolts will appear across our analog meter movement. The foundation of this design lay in the fact that when we have resistors in series, they form a voltage divider. So what we want to do is put a resistor in series with our meter. The output of this voltage divider is the voltage across the meter. And so when 10 volts is put in here, only 78.08 millivolts is on our output resistor, with the current through the voltage divider being the current through the meter, or 101.14 microamps. This series resistor is called a multiplier resistor because it multiplies the voltage necessary to get a full-scale reading on the meter movement. In our case, it's going to multiply it by around 128 times. Now, let's calculate this multiplier resistor. So we're creating a voltage divider, which has this formula associated with it. The output voltage is equal to the input voltage times the output resistor, all divided by the sum of the input resistor and the output resistor. But in this particular case, we recognize that the output voltage is the voltage across our meter, this 78.08 millivolts, which is the same as the current full scale times the internal resistance of the meter. And the output resistor is the internal resistance of our meter here of 772 ohms, and the input resistor is the multiplier resistor that we're going to be calculating. So if we put all this together, we get this formula. The voltage on the meter is equal to the voltage input to our box times the internal resistance of the meter, all divided by our multiplier resistor value plus the internal resistance of the meter. But if we play some magic mathematical game, we can solve for our multiplier. And here's the equation. The multiplier resistor is equal to the voltage into our box divided by the full scale current of our ammeter minus the internal resistance of the ammeter. And in our particular case, we want a 10 volt full scale reading. We have our meter's full scale is 101.14 microamps, and we subtract the 772 ohms of internal resistance, giving us a multiplier resistor of 98,101 ohms, or 98.101 k-ohms. Now, we should always be concerned about the power dissipation of our multiplier resistor as well. So we take the full scale current of our meter, we square it, we multiply it times the multiplier resistor value. We get 101.14 microamps squared times 98,101 ohms, and that gives us about 1 milliwatt. So it's really totally inconsequential. However, there's another aspect that we have to be careful of. Now, we generally think of capacitors as having operating voltages associated with them. But believe it or not, resistors also have an operating voltage associated with them. This has to do with their physical construction to prevent arc over more than their power dissipation. Now, if you're going to be creating a voltmeter for measuring higher voltages, be sure to pay attention to the operating voltage reading of the selected resistors and make sure that the voltage across your multiplier resistor does not exceed that value. All right, let's go find some resistors for our voltmeter design. If we go out to the various sources for resistors, we're not going to find a 98.101 k-ohm resistor available anywhere. So what do? Well, we could play fixed resistor games with stuff like we have, series and parallel resistors until we get the value we want. I mean, for instance, if I use a standard 249 k-ohm resistor and put it in parallel with a standard 162 k-ohm resistor, I get a total resistance of 98.146 k-ohms, which is just 0.045% away from my ideal target value of 98.101 k-ohms. But this doesn't give us the ability to adjust anything. We could choose to use a potentiometer to accomplish this goal. This way we can easily get the exact value we want, and we can calibrate the meter as needed. We want to do this in a way that gives us the greatest control over the actual value to make the adjustment easy. What do I mean by that? What I mean to say is that we do not want a method where you stick your screwdriver on the adjustment pot and carefully think too hard about turning it and it overshoots it in one direction or the other. So simply using a potentiometer as the entire multiplier resistor is not a good idea, because it can be easily adjusted too far in one direction and totally fry your meter. And it makes adjustment a lot more difficult. So what we want to do is use a fixed resistor in series with our potentiometer as the multiplier resistor. We can define how much adjustment room we want to give ourselves. The smaller the adjustment room, the easier it will be to adjust, but also the more likely that we will run out of adjustment before we get to the value we want. For the sake of this demonstration, let's say that we want to be able to adjust to the meter's full scale plus or minus 10%. So how do we do this? Well, we do our multiplier resistor calculation twice. Once for the minimum at minus 10%, and once for the maximum at plus 10%. So this is our base equation here. Our multiplier resistor is equal to the voltage in divided by the full scale current minus the internal resistance of our ammeter. So at our target voltage minus 10%, it's 9 volts divided by our full scale current of 101.14 microamps, subtract out the 772 ohms of the internal resistance of the meter, and we get 88.213 k-ohms. Now that is the value we shoot for the fixed resistor. The potentiometer is at its lowest value, or close to 0 ohms. And now we have the target value plus 10%, or 11 volts, divided again by our current, subtract out our internal resistance of the meter, and we get 107.988 k-ohms. This is the value of the fixed resistor plus the value of the potentiometer adjusted to its highest value. The difference between these two values is the value of the potentiometer, or 19.775 k-ohms. If we simply do more math wizardry, the calculation for the potentiometer is a bit easier. And so we end up with this. The value of the potentiometer is going to be equal to the voltage in times 2 times the percentage expressed in decimal. So 10% is 0.1, all divided by the full scale current of our meter. So in our case, we have 10 volts as our target voltage, times 2 times 0.01, because we're doing 10%, all divided by 101.14 microamps. And guess what? We get 19.775 k-ohms, exactly the same value we got before. Now, let's see if we can find some off-the-shelf parts to realize this particular design. Well, the fixed resistor wants to be 88.213 k-ohms. Well, this is not a standard resistor value, so we look for what might be as close as we can get. While there are 88.2 k-ohm through-hole resistors listed on my favorite distributor's website, if I click on In Stock, watch what happens. There's nothing there. They're not in stock. So the closest value I can find that is in stock is this 88.7 k-ohm, which is only about 0.6% away from my ideal value, and that certainly is good enough. The potentiometer wants to be 19.775 k-ohms. So it looks like a 20 k-ohm potentiometer will do. To make it easier to adjust, let's see if we can get a multi-turn potentiometer. These are called trimmer resistors and are generally intended to be mounted on a circuit board. And so I selected here 25 turns. So with these selections of 20 k-ohms, 25 turns, multi-turn, now that leaves me with 16 to choose from. So I'm going to go with this one here. And here we are, $2.41 for our little trimmer resistor. So the total cost of my multiplier resistor is under $3 plus shipping. What else can I buy to make it worth ordering it? But I don't want to go out and buy all of this. I have plenty of stuff in-house in my junk box. I was able to find a 91.9 k-ohm fixed resistor and a 20K multi-turn trimmer potentiometer. Now, power dissipation in this particular case isn't an issue, and with a 10-volt full-scale reading, I didn't have to worry about the voltage reading. These will do the job just nicely for my experiment. And now that I have my parts, we're ready to start putting things together. When we connect our potentiometer, we want it to act so that when we turn it clockwise, the resistance value is going to decrease. That way, when we turn the value clockwise, the needle is going to move upward as opposed to downward. It makes it more of an intuitive control, because we're turning it up, we watch the needle increase. Now that we have our multiplier resistor created, we need to do the initial adjustment. I will connect it up to my DVM and then adjust the trimmer until I get the ideal calculated value as measured on the DVM. So we're shooting for 98.1 k-ohms. So as we turn clockwise, the value should go down if we set this up right. There we go, 98.1 k-ohms. With the multiplier resistor created, we are ready to put it all together and test our design. The object of what we're going to be doing here is to see how our analog meter agrees with our DVM. Before you do anything else, make sure that your meter is properly zeroed. So what are you going to need to do this? Well, you'll need a variable power supply capable of at least a little more than your target voltage. In our particular case, that would be 10 volts. We're also going to need a DVM capable of measuring our target voltage. I'm going to be using my Tenma DVM, which is rated at 0.5% accuracy for DC voltage. Before you begin, turn the power supply output voltage all the way down. Caution! If your target voltage meets or exceeds 60 volts, then be sure to take appropriate high voltage precautions to prevent yourself from getting shocked. Now let's connect everything up. We've set the DVM to measure volts on the appropriate scale. We connect the positive side of our power supply to one side of our lovely multiplier resistor. That same side of our multiplier resistor is connected up here to the positive input of our DVM. The other side of the multiplier resistor is connected to the positive side of our meter. The negative side of the meter is connected up to our DVM. And then it's also connected up to our power supply negative. Now we're all ready to begin our testing. And now we're going to turn on our power supply and slowly begin to bring our power supply voltage up while watching the meter movement and the voltage on our DVM. The object is to get a full-scale reading on our meter, and as you approach, remember, you got to go slowly and then tap on the face of the meter movement to dislodge the needle just enough so that it can settle into its final position. Let me tap on that meter. That looks like a genuine 10 volt full scale reading, and so we want to write down the value that we have on our DVM, which is 9.86 volts. I determined that this is 1.4% low, and I would like to get it a lot closer. So what I'm going to do now is I'm going to increase my power supply until my DVM reads exactly 10 volts. And then I'm going to adjust my multiplier potentiometer until I get a full scale reading. So I have to be careful not to touch the terminals of the resistor here. And we want to turn this down. We have to remember to tap on the meter face as well. There we go. We have 10 volts on the meter, and we have 10 volts on our DVM. Now we have a voltmeter which is capable to read 10 volts full scale, which agrees with our DVM. Now, analog meter accuracy is rated at full scale reading only, not necessarily at places below that. You might choose to check out other places on the scale and adjust the multiplier resistor as needed to achieve the best accuracy everywhere, not just at full scale. Well, we've done it. We now have a voltmeter with a 10 volt full scale reading, and it was a relatively painless project to do. If you found this video helpful, do click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, toodle-oots.